Okay, guys, welcome back. This is day 4 of simple harmonic motion. And I remember in the last class, dealt with all the kinds of velocity, acceleration, displacement equations in different forms and different styles. We have a really good clarity about the phasor, but yeah, let's look at this diagram also. Like, let's look at this phasor also. So what we did is I took a phasor which is starting at 0 degrees, and I took the SHMs which are both x-axis and y-axis. I considered both. You can look at them both at the same time. Uh, you look at them, how they're moving. You can clearly observe when it is starting from 0 degrees, when we are starting it from 0 degrees, on SHM on the x-axis is starting from the positive extreme already. SHM on the y-axis is starting from the mean position. So after a time, if I have to write the SHM equation after any time, if I have to write the SHM equation for this SHM, it is starting from the extreme already. So we consider this thing as a cos omega t. So remember, every time you have an SHM which is starting from the extreme position, you write it as a cos omega t, and you have an SHM which is starting from mean position, you represent sine omega t. But don't confuse this thing with the horizontal and vertical SHMs. Okay, all the horizontal, vertical, at an angle SHMs are also there. You will look at some SHMs which are like this also at an angle. Okay, so don't confuse yourself with vertical SHM and horizontal. Any SHM can be linked with any of these two. If the SHM is starting from mean position, link it with the this axis. If it is starting from horizontal, I mean like extreme position, link it with this thing. Don't link it as if it is a vertical SHM or a horizontal. Don't say that. Okay. If a block is oscillating like this, you can link it with both the axes. If the block is oscillating like this, you can link it with both axes. If a block is accelerating at an angle, simply turn the phasor in whichever the angle that you want and try to relate it. Okay, you don't have to link these vertical and horizontal with any SHMs. Okay, any SHM can be linked with any of these axes. If it is starting from mean, it is a sine. If it is starting from extreme, it is a cos. That's it. It's as simple as that. I'm giving you a one more peek at this thing. Look at how it is moving. I think it has two rotations, I guess. Acha, no, there's only one. The time runs from 0 to 6.28 seconds. So it's around two rotations he's giving. Okay. So just an understanding again, remember this thing. Now, once this is over, I want you people to take ourselves to the next idea. Aditya has a doubt already. Aditya, what is it?
Angular frequency or omega has a limitation, sir.
What kind of a limit?
Like at because whenever we are turning, like it's like we are restarting the SHM. Like, so is there any kind of limitation from this to this? We have to put the value,
I don't think
omega
so.
value.
No. I don't think so. Omega just decides what the frequency, that's all. There is no such thing as a limitation where you have to keep this much omega, that much omega. No, I don't ever see that. There are some problems. When we get to the problems, you'll understand the importance. Okay. Now, let us look at the energy now. Let us look at the energy. Remember, yesterday I already asked you to link the whole idea to a spring block system Km. So if I pull the spring block system to a distance Z, we've already written the equation of SHM as Z is amplitude. So Z is amplitude Z. Since SHM is starting from the extreme position, I'm starting my T. I watch it. I pull the block and I started it at the extreme position. So you write it as cos, and you can write it as sine omega t plus 90. Anything is fine. So wait a second. Mm, yeah, cos omega t plus 0, or you can write it as sine omega t plus 90 degrees. Let's do it that way. Z sine omega t plus 90 degrees. Now in the place of sine, I have to write, sorry, omega, I have to write root over k by m, because I didn't mention omega, but I gave you root over k by m. Somebody gives you a problem like this is how you represent the SHM equation. No. I wanted to introduce energy before I wanted to talk about this only. But if we have a spring block system, it is a lot more easier for you people to understand the energies of the system. It is oscillating. The spring block system is oscillating. Can somebody tell me the energies of the system as if when the spring is at natural level, like when the block has the maximum speed, we've already known this thing. Let me take a new page and clearly explain it. The block is oscillating. This is the main position. This is minus A. This is plus A. Everything is in place. We all know that at this point, Aniket has a doubt. Aniket, what is it?
Not doubt, sir. We can just use the normal equations, right, sir? Half kx and
Exactly.
square
Yes.
and
Yes.
put it.
Yes. Yes. It since it is coming from you, that's what I wanted. Like I directly want it coming from you. Instead of like in the textbooks, what they do is they again try to find the energy doing like force, a restoring force, the work done by restoring force and all. They again come back to the same point. They write the kinetic energy, potential energy separately and put it in specific terms. But you people are already good at it. Like the spring, the block has a maximum kinetic energy, maximum speed at the mean position. When it goes to the extreme position, the speed is zero. When it goes this extreme, the speed is zero. So I can clearly write the kinetic energy as half mv square here or half mv max square here. I can write the kinetic energy zero here. I can write the kinetic energy zero. You have any problem with these kinetic energies? I don't think so. I can in fact extend them and write this is zero. This, do you remember the Vmax value as A omega? Do you remember the Vmax value as A omega? Like in an SHM, in an SHM oscillating at the mean position, the maximum speed is sorry, A omega. Did I write V omega? I'm sorry. Vmax equals to A omega. So the kinetic energy can be written also as half m A square omega square at the mean position, at this position 0, at this position 0. Simple to write the kinetic energies. Let us write the potential energies. I can clearly say at this mean position, at the mean position, the potential energy is 0. The spring is not compressed, the spring is not expanded, so the potential energy is 0. At the extreme position, the spring has expanded up to plus A. So the potential energy is nothing but half K A square. At the negative, it is half K minus A square, which is again half K A square. I hope it is clear with Aditya. Yesterday he made a mistake this. Okay, so this is half K A square, this is half K A square. At the mean portion it is 0. So let me put it all in a single box for a block of mass M, which is executing an SHM in between plus A and minus A and mean position. The kinetic energy, here it is 0. It is half m omega square A square, 0. The potential energy, half K A square, half K A square, and 0. Half K A square and 0. Can you people observe one thing? We have an observation here. Do you have any observation? Anybody raise your hand and say anything?
The
Yeah.
m omega square is equal to k.
Exactly. This m
Yes,
omega
sir,
square is
exactly.
basically k. Our k is nothing but m. We already have this omega equals to root over k by m. So if I square it, k square into m equals to, so m omega square is nothing but k. So let me delete this thing. Let me delete this part. Let me remove k and write the potential energy is nothing but half m omega square a square, half m omega square a square. So the important point is it is the kinetic energy that is getting into potential energy and again kinetic energy and again potential energy and again kinetic energy and potential energy. So it is just a variation of potential energy and kinetic energy constantly. When a block is oscillating, it's the potential energy and kinetic energy that is constantly varying. Let's so like when you look at a Sharath and Aditya, you have doubts?
No, sir.
No,
Like I
sir.
actually wanted to answer it, sir.
No. So
Yes, sir.
when a block is oscillating, it is the kinetic energy and the potential energy. When it comes back, it is kinetic energy, and when it goes here, it is potential energy. So it is coming as kinetic energy and potential. So it's just a energy transfer between the block and the spring. The spring and the block are constantly exchanging its energies in between. It is taking the energy and it's giving it back. It's taking the energy and it's giving it back. So even the energies are oscillating. The values of energies are also oscillating. We will talk about it, but let's look at the values. The kinetic energy, the potential. Why don't we like? Yeah, did you not get doubt that? Yeah, we only found it at the mean position, at the extreme position. Yeah, everything is fine. But what about this is mean plus
Some
A
random point.
minus A. We all have all the energies like mean position, extreme position, potential energy, kinetic energy. What about some random position?
So we'll take that measure of x and
So
that
we'll have to
speed
take
and time.
delta, sir. We'll have to take delta into consideration.
What delta?
X, sir. Here in this case, X.
You meant
Take the
X.
difference.
So at some position, like let me take the spring block system only. That is a far more easier way to understand for you. Okay, a spring block system. This is a mean position. This is a minus A. This is a plus A. The spring block system, at the extreme positions, at the mean positions, we know the speeds, but at some random X, it has some V. Okay, at this position, I want the energy. At some
So the
random
energy
point,
is
I want
gonna
energy.
remain constant, sir. The
Yeah.
energy is gonna remain constant for whole movement, sir.
What?
Energy will be constant, sir. Total energy will be constant.
Yeah,
So
I
we will
know.
find the potential and kinetic energy at that point and equate it to
Okay,
total energy, and
let me
what
check.
we want, we'll get it.
Okay. Let me check that. Will you please let me check that? Will you please? I'm
Yes,
begging you.
sir.
Yeah, thank you. Thanks for your permission. So the potential energy goes like half kx square. The kinetic energy goes like half mv square. Okay. This is the total energy. This part is potential. This part is kinetic. Okay. Now, shall we look at this thing in much deeper sense? Half kx square, half m. V is nothing but, do you remember the expression for v at any point? V equals to omega
Yes,
into
sir.
root over a square minus x square. I'm going to put it there. So omega into root over a square minus x square whole square. So if I expand it, the total energy half kx square plus half m omega square into a square minus x square. I can leave it like this. I can bring it in this manner. Let's do it in this manner. Half kx square plus half m omega square a square minus half m omega square x square. Again, k is nothing but m omega square. So this term simply gets cancelled. That total energy is coming as a constant value. The mass is constant, omega is constant, a is constant. So the sum of the total energy is always constant. Okay, people would like to write this in another form. In fact, half, I'm just writing it here. You can do it. In the place of x, a sine omega t. In this place of v, a omega cos omega t. Do you remember these equations, guys? The displacement equation as a sine omega t, then velocity equation as a omega cos omega t, and acceleration equation as a minus a omega square sine omega t. Like we've done this thing already, right?
Yes, sir.
Out.
Sir, even delta included in that.
What delta are you talking about? I don't understand where you're bringing this delta from.
Sir, right now maybe we don't need, but
Acha, you're talking about that additional delta. Yes.
yes, sir.
Yes, sir. That's what
Oh,
I
you
was
can
talking
take it.
about
You
previously.
can definitely take it. I don't consider that because most of the cases I just take that as a zero value. Like who cares? Okay. If it is there, I'll just add it, put in there and take an extra value and do the calculation. But most of the cases we don't need it. Okay. There will be times when you will be needing it. This is not the time for that. Okay.
Okay, sir.
Yeah. So let's move on. Yeah. Like when I have this thing, sine square theta and cos square theta, when I write it again, I get the same value, half m omega square a square. So this is the idea, guys. The total energy is always like there is a kinetic energy and potential energy. These values definitely vary in between each other. The values are definitely constantly varying in between each other. but the total energy is always constant. Okay, to put it in a much a neat sense, let us write it actually that way. Okay, the kinetic energy is half mv square plus the potential energy is half kx square. Let me clearly expand this thing. This is a omega cos square omega t. This is in the place of k, I'm putting m omega square again. In the place of x, I write a sine omega t.
Sir, you forgot to square a omega cos square omega t, sir.
Sorry. Okay, so I'm getting half m a square omega square cos square omega t plus half m omega square a square sine square omega t. You can clearly see this value is varying with time. This value is also varying with time, but the summation is always a constant value. This is an important thing that you people need to learn. Okay, like they will ask you problems like what is the kinetic energy, what is the potential energy, and what at what position, like in the beginning of the class, who asked that question here? I think it is Vamshi. He asked a point at the main position, you know, it is all kinetic energy. At the extreme position, it's all potential energy, it's all potential energy. But he is asking at some point, at some random point, where there is x and there is some v, they give you like kinetic energy and potential energy are equal, or kinetic energy is 2 times the potential energy. So at that some point, you write the potential energy, you twice it, equate to kinetic energy, you try to find the position. That's it. Okay,
Excuse me, sir.
yeah.
So in that previous equation, we can cancel out sine square omega t and cos square omega t, right, sir? Because there are some.
Yeah, that's what I said. Like when you add it, you get sine square omega t plus cos square omega t as 1. So you'll get half m omega square. That's all.
Yes.
You didn't get that point. Clearly, this value is varying, this value is varying, but when you add it, you get cos square theta plus sine square theta, so which is actually equal to 1. So you will definitely get only half m omega square a square only. That's all. That is the total energy. Like I just shown you here. This
Yes,
is one way to put it. This is another way to put it. It doesn't matter which way you take it, you'll always get the same idea. And then, okay. So what was I saying again? Yeah, so there are some questions on this, just the potential energy and kinetic energy sometimes. So it is up to you people how to do these kind of problems. Now, I want you to look at this little thing. Look at this diagram. Yeah. A spring block system again, it is oscillating. As it is oscillating, they clearly give you the graphs for potential energy, kinetic energy, and total energy. I wanted to draw it, but look at it. It's quite clear. Like I'll just show one by one. Okay. This is the potential energy. 0, negative point maximum, coming back to the original position 0 and coming back, going to the extreme maximum. Let's only look at the kinetic energy. If you want me to change the values, we can change the values, but yeah, look at it. This is how the kinetic energy is changing. If you people observe, this is a graph for cos square theta or sine square theta. I'm not sure if you've already known the graph for cos square theta or sine square theta.
yes,
This
sir.
is how exactly it looks like. The graph for cos square or sine square looks like this. And looking at the total energy graph, it never changes. Okay. So the best part is the summation of these two values always remain constant. You can take at any point. You can stop at any point. Let me check if I can vary the time in no, I can't. Look at this point. Look at this point. Like look at any point. You can pause the diagram at any point. I think it is, no, this is not available in ophysics.com. It's just available here.
Because they both meet at 2 points.
Yes, exactly. So that is the point where the potential energy and kinetic energy are equal. Okay, there is a point there definitely. I'll try to pause it there. Yes, almost there. Yeah, I did it. No, I still didn't do it. There is a little difference, but yeah. So at that specific point, the kinetic energy and potential energy are equal. And they might ask you, what is this position? Like, how far is this thing? What you need to do is, all you need to do is half kx square equals to half mv square. Do this thing. In the place of v, you put root or omega into root or a square minus x square whole square. Try to solve this thing. You'll get the value of x. I
One
think you
small doubt, sir.
a by root. Yeah.
So how should we know which of those 2 points we are getting?
You don't. At both the points, it is happening. So you don't really know which point it is. You'll never know.
Okay,
You're
sir.
talking about
Yeah.
energies, right? So it doesn't matter which direction you're talking about. So if somebody says there is a point where the potential energy and kinetic energy are equal, he's referring to both the points.
Okay, sir.
He has to mention whether which point is this. Okay, you have to do it. Otherwise, you don't know. You never know.
Okay, sir.
Vamshi has a doubt. Vamshi, what is
Sir,
it?
at the middle, the kinetic energy and total energy will be equal, right, sir?
Yes, yes, yeah. At the middle, it's a thought. It's completely kinetic energy. Like there is no potential. If this is zero, the sum is only kinetic energy, which is also equal to total energy. Total energy equal to
sir.
kinetic energy plus zero at the middle.
Yes, sir.
At the extreme portion, total energy equal to zero plus potential energy. At this
Yes,
extreme,
sir.
total energy equals to zero plus potential energy.
Yes, sir.
You get that?
Yes, sir.
And this graph is like quite important. There are questions on this graph sometimes. I often find some questions on this graph. So be careful with this graph. Sometimes they give you silly questions
Sir,
on
we
that.
don't need the other side, right, sir? While solving sums, only one side is enough.
If both answers are in the solution, I mean like in the options, you have to go for both.
Okay, sir.
Okay. So they might ask you any kind of a question, you should be ready to give the answer. All right. So this is with the energies, guys. This is how you find the energies. Now there is more to talk about energies, but we will come back to this thing after I finish one of the important topics in this thing. I'll tell you what they do. They simply give you a problem. Like yesterday, I gave you this problem, mx, and I pull it to one extreme by a distance capital Z, and I asked you the equation of SHM. So you people gave me the equation of SHM. You can write it as x or y equals to amplitude capital Z sine, in the place of omega you wrote root over k by mt plus 90 degrees, since it started from the extreme. This is how you give it. And somebody might ask you the time period, let us say. We already learned all the equations, all the relations between time period, omega and f. Omega, time period and f yesterday. If you remember them correctly, omega equals to 2 pi f or 2 pi by t. So from this I can write time period equals to 2 pi by omega. You have an issue with that, Vamshi?
No, sir.
Time period equals to 2 pi by omega. We already know the omega value. So time period, it can be written as 2 pi root over k by m. So you write it as 2 pi root over m by k. The problem is in SHM, when we are dealing with the SHM problems, they don't ask you the equation. They often trouble you with just finding the time period, because everyone can write the amplitude, everyone can write the phase angle. It's always the trouble is always at this point. And yeah, what's so wrong in this thing? Yeah, it looks so simple, right? Yeah, for a spring block system, it is very simple. Whenever they give you a simple spring block system, whatever you have, you simply write it as the time period of the spring block system is 2 pi root over m by k, right? Yeah, 2 pi root over m by k. That's it. What if the SHM is not just a spring block system? We already talked about it. There could be millions and types of SHMs. There could be different types. This is just one of those types. In this one of those types, I have m, I have k. I clearly found the time period and I have the answer. That's it. But what if they give you different styles, different ways to give you a problem? Now, before giving you any kind of a problem, I'm telling you how to solve this problem. Let us approach. We always have to find time period. Follow this process, guys, clearly. Now, to find the time period, they always ask you to find the time period. To find the time period, you always need omega. You always need omega. Remember where we got the omega from? We got the omega from minus omega square x. This is where we got the omega from. Now, how do you find the acceleration? You find it from the force. So every time they give you any kind of a problem, no matter what kind of a problem they give you, they ask you time period. To find the time period, you need omega. To need omega, you need acceleration. To find acceleration, you need force. So every time they give you a problem, no matter what kind of a problem, you always Look for the restoring force. This is the most basic thing. If any of you people ever ask me a problem to find the time period, and I ask you in return what is a restoring force, and you don't tell me, you're done. I'm not teaching you anything anymore. You're striving, you're trying a problem with time period, you're trying a problem with uh, somebody is giving you a problem, ask you to find the time period. The first thing you should do is find the restoring force. Let us say I slapped Aniket really hard and Aniket started oscillating. Okay, now I asked you the time period. You don't go console Aniket. The first thing that you should check is, why is Aniket oscillating? What could be the restoring force which is bringing him back? Every time the man is oscillating, what could be the restoring force which is bringing him back? That is the first thing that you should look, and that is that is how the problem is solved all the time. Okay, I give you another. I give, like, raise your hands. I want some of you people answering these questions. Aniket, Aniket, if I slap you and you oscillate, what could be the restoring force? Aniket.
I'm thinking, sir.
It's
Sir,
just
I
your
have one
flexibility in your
answer.
body, like your flexibility, the
Oh,
muscle
I
force
was
is
yes,
saying
sir.
rigidity.
it's just that force that is bringing you back. That's all. Okay. I
Yes,
have
sir.
a guitar string. You pluck a guitar string. A guitar string is oscillating. What is causing it to oscillate?
The rigidity in the string, sir.
Exactly, the
Rigidity or
elasticity, or whatever you call it as,
yeah.
the elasticity in the string, it is making it oscillate. So that is the elastic force that is making it oscillate. Now, like in the beginning of this topic, I given you a problem. When a ring is there and I put a mass here, it obviously oscillates in between. Who is causing the restoring force?
Gravity.
Gravitational
Exactly. So all
force,
you
sir.
need to do is find the restoring force. That's all. How we do it, we'll do later. Okay. But every time they ask you the time period, the first thing that you need to do is take it away from the mean position. At the mean position, you'll never find the mean, what do you, sorry, the restoring force. At the mean position, the restoring force is zero. So always take it away from the mean position by a small displacement x. Always take it away from the mean position, small displacement x. Then check for the restoring force. And once you have the restoring force, you have k, you have omega. Once you have omega, you have time period. This is how you need to
Excuse me,
solve.
sir.
Yeah.
But
So one small doubt, this flexibility, sir, it's always constant, the force.
In your case, maybe not. In reality, no. But in most of the problems that we do, it is constant.
Okay, sir.
Yeah.
sir, one more
Now,
thing, sir.
yeah.
Excuse me, sir.
Yeah, who's
So,
this?
but this is not SHM, Aditya, sir. But that was not SHM. So, how are you going to find time t period using those formulas?
I didn't get you. I didn't get your question. Can you come again?
Like the movement of this mass m in that ring, sir, due to gravity.
We don't know
It's
whether it
not
is
an
an
SHM,
SHM
na,
or
sir.
not. We don't know whether it is
But it is not
SHM or not.
SHM.
I don't get you. We still don't
Like it is
know.
not an SHM. So, how are you using those formulas here?
Yeah, we still don't know whether it is an SHM, but guess what? This will be an SHM. You will see that. You will see that as we move on to the problems, you will actually observe that this is an SHM only. Okay. Yeah, I've already given this problem in the past in the first or second class, but this actually is an SHM. We
Yes.
will actually prove that. Once we get there, we do that. Okay. Let's start with some easy problems. Okay. Let's not burden ourselves with heavy problems. Let's start with a very easy problem. A spring and a block. Why a single spring? We've already done with a single spring. Guys, you have to stay.
Yes, sir.
Let me take two springs. Now this is a mean position already.
Sir,
Okay.
same problem we had in kinematic.
Yeah, but we didn't do the time periods then. We only did
Yes,
the
sir.
restoring force only. Now
You
look at
told to
it.
hold it, sir.
Now to find the time period, step by step, I'm reminding you to step by step. What's the best thing? What's the first thing you should do?
The
Find the
restoring
restoring
force.
force.
No, you should disturb it first. If it is not, if it is at the mean position, there is no restoring force at all, right? So
Yes.
disturb it by
Yes, sir.
x. Now check what is the restoring force. What will be the restoring force? There is k1x from this,
Yes, sir.
and
And
there
one
is,
minus K2 extra.
idiot, it's in the same direction only.
It's in the same direction.
So the total restoring force, F restoring here is nothing but K1x plus K2x. Since both are in the opposite direction of x, I put a minus there. You all agree?
Yes, sir.
Yes,
Yes,
sir.
F
sir.
So we can
restoring,
just put K1 plus K2, right?
yeah,
For everything.
that's what I'm writing. F restoring equals to minus of K1 plus K2 into x. So mass into acceleration, K1 plus K2 x, acceleration equals to minus K1 by K2 by m x. Once you have omega square, you can write the time period as 2 pi root over m by K1 plus K2. So this is the time period. Do you get it? Now,
Yes,
Yes,
sir.
sir.
So this is no different than the one spring one, just with K1 plus K2 if we keep K
exactly.
as.
But I'm going to give you a problem. Try to immediately intuitionally answer it. Okay.
Okay, sir.
Time period.
Same thing
Same
again, sir, with
Same.
K1 plus K2.
I thought you people would say K1 minus K2. But you
So
didn't.
same formula. No?
The same thing.
It'll be the same answer.
Yeah.
So it is way more easier than
No,
that
no,
for
no. I
me.
was expecting Aniket would actually say K1 minus K2.
No, sir.
Now, again, the same thing, since it is expanded, you will get K1x, you will get K2x. So the total restoring force, F restoring is nothing but minus of K1 plus K2x only. I'm not writing all those steps. I'm directly writing the time period 2 pi root over m by K1 plus K2 only.
So for this, sir, we'll just have to find the resultant K, right? Like for these kind of problems
People
for
do that.
finding time
People
period.
do that. The resultant diagram of this thing, people often write it as a single spring whose constant is K1 plus K2. People do that. You can do that. Okay.
Yes, sir. It's more easy to
It's
look
much
at the
easier, sir.
diagram.
Yeah, I know.
Sir, like my doubt is like, can we use the same thing? So like finding resultant K every time,
Finding the resultant K every time.
every time,
Yes,
But
sir.
it depends on problems.
like for
Not
all.
all problems are as simple as this. Okay. Like sometimes problems get a lot different. Let's look at some problems. Okay. Shall we?
Yes, sir.
So there won't be any three spring systems, sir. Like they are in the triangular format.
Ah, there will be
Okay.
triangles. There will be squares. There will be all kinds of
There's
systems.
one such question in HCM.
So
What's
those
the
will not
answer?
be
Sir,
SHMs, right?
What's the answer?
K1 plus K2
This
plus
K2
K3,
plus
sir.
K1
K3.
plus
the
K2
K3,
minus
sir.
K3.
The time period is directly 2 pi root over m
K3, sir.
by K1 plus K2 plus
Plus K2
K3.
plus K3,
K3.
sir.
No difference, right? No.
Yes, sir.
No difference, sir. Just we added one more K3 there.
This is where
Sir,
it gets
what if the
tricky.
body in vertical?
Oh, that's a good question. We will get there. We'll get there. This is where it gets tricky.
So same,
So
sir.
again,
2
same
pi
thing.
root over m upon K1 plus
K1
K2.
plus K2.
Nope. That's where
So
the
K1
problem.
minus K2.
That is where the problem is. Let me draw it again. It's a new page. So this is where the problem is. You have to follow and stick to your basics extremely, like rigidly stick to the basics that I've just told you. What's the first thing you should do?
Find the restoring
Displace
force.
force.
Like displace it and then find the restoring
Displace
force.
it by a displacement x. Now, when this moves by x, this spring expands to some extent and this spring expand to some extent. So I call expansion in this thing as x1, expansion is this thing in as x2.
Excuse me, sir.
Yeah,
So can we do this like how we used to do F minus T is equal to MA like that?
we are going to do that. Don't worry.
Yes, sir.
Now, expansion in one spring is x1, expansion in the second spring is x2. I can clearly say the sum of these expansion is nothing but x, right? It's like it expanded 2 centimeters. If it expanded 3 centimeters, obviously the block will move by 5 centimeters only, right?
Yes, sir.
So
Yes,
that is
sir.
the first thing that I did. Now, everything I'm doing is, it should be intuitional only. I'm not teaching you any new Newton laws, okay? I'm just doing the same thing, x1 plus x2 equal. Now, the first thing you should be doing is, you have to find the restoring force. Who is pulling the block backwards? This thing.
Yes, sir.
Now
Yes.
this
Yes,
thing,
sir.
let us call it some force. Can I equate that force with the force in the spring?
Yes, sir.
Now,
Yes, sir.
we already know that this is K1 and this is K2. And the spring is only expanded by X2. So the spring force here is K2 X2 only.
Yes, sir.
Yes, we did half of the job. The restoring force is minus K2 X2. Now, the problem here is, like, be very careful here. We just found the restoring force. That is good. That is clean. No problem in that.
What
But
about
that's what one
K1?
spring, sir.
But the restoring force must be always proportional to the displacement of the body. So it should be proportional to x. Is it proportional to x here?
Yes.
No, it's not. It is proportional to x2. It's not x.
Acha, X2, like, okay.
Exactly.
I
So
was thinking normal displacement.
no, no, no. You should be writing the restoring force in terms of x, not x2. Good that you already found the restoring force. You're following the logic. This is how the problems can get twisted. Like I said, the problems can be really easy, but the problems can get twisted also. So I have the restoring force in terms of x2, but I want it in terms of x. So this is where our fight is going to be. I already know x1 plus x2 equals to x. And also tension in this thing. This is k1 x1, this is k2 x2, and they are connected. So from that I can also write k1 x1 equals to k2 x2. So I have another expression saying k1 x1 equals to k2 x2.
I didn't understand why, sir.
Because it is they're directly connected. There is no mass, there is nobody accelerating. So if they're connected here, the force on this side and the force on this side must be equal.
Okay, sir.
So k1 x1 equals to k2 x2. So I'm going to use it. I'm going to use these two and find some relation. Let me show it to you. In the place of x1, I can write k2 x2 by k1. So I'm going to put it in there. K2 x2 by k1 plus x2 equals to x. So I'm going to take out k2 by k1 plus 1 into x2 equals to x. I have x2 equals to x by 1 plus k2 by k1. Now what am I going to do with this thing?
Put it there, sir, in
Exactly.
the above equation.
There, f restoring equals to minus k2 into, in the place of x2, I'm going to put the whole thing, x by 1 plus k2 by k1. If I simplify it, I get the restoring force as minus k1 k2 by k1 plus k2 into x minus k1 k2 by k1 plus k. Now this is the effective k. So the time period simply be 2 pi root over m by k1 k2 by k1 plus k2. Now you don't have to do this process every time. You can simply remember it as if when two springs are in series, this is an effective spring constant. When they are in
There is
parallel,
like
yeah,
there is like the effective resistance in
but in the
parallel.
opposite, like in the opposite way. Okay, like when the
Yes.
So,
springs are in parallel, like they're parallel like this. This is parallel. Guys, remember this is also parallel. This both the cases are parallel only. When you have it, k effective can be simply written as k1 plus k2,
Plus k2.
and the springs are directly connected. In series, the springs are directly connected to each other. You write this k effective as k1 k2 by k1 plus k2.
so one small doubt.
Yes.
In the previous one, still we have the same thing, right, sir? K2, X2.
Which problem? Like previous problem?
Yes, sir, this one.
Let's check. Let's check. Yeah. I
No,
don't.
sir, the one you just did.
Okay.
Yes, sir.
Yeah. Where?
This value that we got, sir, is still equal to minus K2, X2.
Yeah, it is still equals to minus k to x2 only. But I have the term in terms of the restoring force in terms of x now. Then only I can
Oh,
consider
but
this
we
as
haven't
omega square.
counted the first spring.
No, then only I can
Yes,
consider
sir.
this as omega square. I cannot consider this as omega square because there is no x2 here. Since there is x here, F proportional to X. That is why I can consider this thing as omega square. That is what I'm trying to say. Get
So,
it?
but one doubt in this, sir.
Yeah.
The force acting is still by one spring only, right, sir? If we see in this sense.
Yeah, but you shouldn't write the force in terms of X2. The force should be in terms of X only. Since the body moved by a distance X, the force, the restoring force should be in terms of X only.
Okay,
No,
sir.
sir. I have no. I am asking like you have done this minus K2 X2, right? Right, sir? Yes. Why aren't you counting X1 and K1 X1, sir, here?
Oh, you can take to do that also. Yeah, you can write it as minus K1
So
X1.
why not both together? Both together.
Yes,
Both
sir.
are
Like
not acting. Only
K2
one
X2
force is
minus
acting.
K1 X1.
Because there is only one force is acting on it. Like, let me show. Do you remember from Newton laws? Like the force on this block is only this tension only. If there is another force, do you add this also to this as mg?
No, no, because they
Oh,
weren't
So there is
okay,
only
sir.
one
consider.
spring that is connected. I'm only writing that force only, that spring only.
Okay, sir.
Okay.
Yeah, it is a bit confusing, I know, but you don't
It's
have to
not
confuse.
intuitive, sir.
It is it. You don't have to confuse yourself that much. Try to just remember this point. This parallel and the series springs thing.
Yes, sir. So
Okay.
if we have 3 springs, 4 springs like that.
Like I'll give you 4 springs in series.
Yes, sir.
You'll have to write it. Let me show it. Okay. You have K1, K2, K3. Like what do you do in series? Is 1 by K effective is nothing but 1 by K1 plus 1 by K2 plus 1 by K3. You don't do this
Yes, sir.
when it is in
So
series.
it is just equal to that formula what we used in electrostats for volts, sir. Like
Exactly. Here
we
the
make the
system is
Resistance
K1
for
plus
effective
K2 plus
resistance in
K3.
parallel.
It's like in parallel.
yes for
It's like in
resistance we make.
series. Okay. Don't reverse those formulas. You will get into
It's
a.
like the exact opposite.
Yeah.
So why this 1 by K
Yes, sir.
effective?
Didn't we not do the same thing? Okay. I'll show you this also then.
Yes, no, so like a generalized way of
X.
saying like
X
no matter how many we have.
you move it by x, you will get x1, x2, x3. Now you write x1 plus x2 plus x3 equals to x. You write the restoring force as k3 x3.
K3, X3.
You try to convert k3 x3 in terms of x using all this. You will get this formula only.
Okay, sir.
It's a thing, okay, but you don't have to do it anyway. Okay,
So it will
I
be
just
like
There
wanted
is
to
K1,
the
make
X1
object in
equal
the
to
middle of
K2, X2 is
springs.
equal to K3, X3, right?
too many people talking at once. What is it, Sharath?
So it will be like K2, X2 is equal to K3, X3 is equal to
Yeah,
K1,
yeah, there is
X1.
also that. K1 x1 equals to K2 x2 equals to K3 x3. Guys, whoever didn't understand the series and parallel spring systems, please simply remember this thing. This is more than enough. I see the reason why I taught you that is like you should be understanding the way we are approaching the problem. Okay. If you don't understand it, you're totally fine with this thing. Nobody's going to ask you how you get this and all. Okay. Nobody's going to ask you the proof for that. All right, guys. Now let us look at another problem in this thing, not just spring blocks. There are other problems also, right? There are other SHMs also. Or why don't we do one more stunt here? There is a spring block system and there is some external constant force. So because of this constant force, the spring block system is already compressed here. Now they are in equilibrium. Like everything is in rest. So there is F acting on this side, there is Kx not acting on this side. So the system is in equilibrium. Now I disturb it. If I disturb it by a small displacement, it will oscillate about this point now. Not the original mean position. The mean position has changed. It will oscillate about the new mean position. You're getting my
Sir,
point. The
can
spring
I
I
block
do
say?
not
system
get
is
that
Yes,
in,
point.
sir.
yeah.
So
Now,
again, can you please repeat? I did not get that point. What
like
you told.
the spring block system is not naturally at this position, man. Naturally at this position. Somebody
Yes, sir.
came and compressed the spring, like put an external force and compressed it to a specific point. and
Yes.
everything is
Okay.
in stable, like F is acting on this side, F is acting on the other side, they're stable. If I disturb it now, like slightly disturb it, slightly give an impulse to it, it will start oscillating, right? But it will oscillate
Yes.
about
It
the
will
new equilibrium. This is a new equilibrium position. This is the old equilibrium position, if you remember that. But this is a new equilibrium position. It'll only oscillate about the new equilibrium. Do you understand that?
Yes,
Yes.
sir.
Yes. Now
Yes,
I
sir.
understood.
Now, I'm asking you, what is the time period in this case?
So 2 pi into root over m by k plus f by m.
No, let us check that. I hope you understand the idea, first of all.
Yes, sir.
The change of equilibrium thing, okay? So, the spring is already compressed because of this external force, and there is some kx naught. Just for fun, I'm mentioning the old equilibrium also, OE. This is NE, new equilibrium position also. Just for fun, I'm mentioning it, but it doesn't really have any meaning. Okay, you can forget that. And about this new mean position, it will oscillate. That's what I said. So about this new mean position, I try to move it by a small displacement x. A small
So
displacement.
half k x plus x naught whole square.
No, don't write the energies. Don't write the energies yet. So small displacement x. The external force is still there. Or why don't we compress it more? Okay, why don't we compress it? It makes more sense for you people. So it's the same thing, but it makes more sense. I'll consider the displacement on this side. So the block has moved a further x from its mean position. So the external force is still acting, and the spring force is now k x naught plus x. So there are three forces, two forces. F is already acting, k x naught plus x is also acting. So if only I write the total net, F net. If I wrote the total F net, let us look at all the forces. F is acting. This is opposite. Let's just call this as an opposite direction. So minus k x naught plus x. So F minus kx naught minus kx. Now, if you remember, F and kx naught are equal basically. I cancel them.
Yes, sir.
F net is simply coming as minus kx. Mass into acceleration equal to minus kx. Acceleration equals to minus k by m into x. So the omega is still the same thing. So the time period is still the same thing. 2
Nothing
pi
has
root over
changed.
m by k.
Nothing has changed, sir.
This is the beauty. So in a spring block system, when an external constant force is acting on the system, yes, the equilibrium position has definitely changed. The equilibrium position has definitely changed, but the time period of a spring block system does not change. That is the beauty of it. Okay, so this is the reason why. Let me give you. If only I have the spring block system vertically. Let us say this is the natural length only. This is the equilibrium position, old equilibrium, which means natural length. But because of mg, there will be a new equilibrium position. So at this position, there will be mg acting on it, and there will be some kx not acting on it. So about this new position, it will oscillate. And what is the time period about the new position? It is 2 pi root over m by k only. Even though an
Yes,
external
sir.
force is acting on it, obviously, yes, the equilibrium position has changed. Instead of oscillating about this point, they will oscillate about this point. The equilibrium position definitely changes. By what value? X naught value. You can find that value also. Kx naught equal to mg. So x naught equal to mg by k. So the equilibrium position shifts by a distance mg by k to a new equilibrium position. Again, it will oscillate with the same time period only. So just because there is gravity existing, or just because there is a constant force existing, external constant force existing, the time period of a spring block system does not change. And this is the reason why they use spring block systems in watches. A spring block system springs in watches for maintaining the constant time period. It is not affected by gravity. It is not affected by any external force. The time period always stays the same. Aditya, what is it?
So is that the force, that constant force is necessary to be conservable, or it can be anything?
No, it has to be a conservative forces only. Okay, if it is not
Okay.
non-conservative, it's not SHM in the first place. The SHM
Yeah,
is
then that was my doubt. If
the
not
SHM will get
SHM, we have to do
SHM will
something
get
different.
disturbed. If it is conservative, yes. Simple point, is the SHM not changing? Is it not getting disturbed? Yes, it is getting affected by simply changing its equilibrium position to a new point, but it's not changing anything else. That
So
is
we can just consider it like a normal spring.
yes, just like no matter like if they give you a problem like this, if I give you a problem like horizontal, vertical, or at an angle, it doesn't matter now. That is exactly what I'm trying to say. So you don't ever consider, you don't ever worry about the time periods when a spring block system is given like this. You don't consider, you don't worry about the spring block systems no matter in which direction. You always have to consider the point that the time period is always 2 pi root of m by k. If there is two springs, you write k1 plus k2. If there is two springs in series at an angle, you simply consider the effective spring constant. Nothing is affected except for the equilibrium position. The equilibrium position changes, that's all.
Sir, one doubt, sir.
Yeah,
If those two springs are at an angle to each other,
great doubt already. That's a good doubt. Shall we let's pursue this question also. Uh, Let me take you through a special case where a block can only oscillate along this groove, but the spring is attached at an angle theta. Okay. Sharath, you have a doubt or you have to say anything?
so we can take component.
There I have a doubt,
Yeah.
not a doubt, sir. So like usually for constant forces, this thing works, right? Like K won't change
Mm-mm-mm.
the time period. So if there's some varying force like friction, then the time period will change.
It's not an SHM anymore. If there is friction, it's not an SHM anymore.
Oh yes.
So you don't even consider that, you don't even bring it here. Okay. All those things come under at the end of this topic as damped oscillations, which is a very tiresome topic because there is a lot to talk and it's not that important also. We will see there when there is time, I will also talk about that. Okay. So yeah, what is the approach for this question when the block is only allowed to oscillate at an angle? Again, we
Components of
follow
the
the
set.
same
We'll
thing.
take sine theta, sir.
We will move it by an x distance. So when the block is moved by x, the spring is expanded by how much? X cos theta only. If you can calculate
Yes.
that. The spring
Yes,
is
sir.
only expanded by x cos theta. So the spring force is kx cos theta. But can I write this as a restoring force? No, the restoring force, the oscillations are in this direction. So the restoring force must be in this direction. So what should I do? I have to take the component of this force again. I have to take the forces component again. So kx cos theta into cos theta. So that makes it the restoring force as k cos square theta x. The restoring force as k cos square theta x. Obviously, you put a minus there. So f equals to minus k cos square theta x. Everything is same. So the time period is simply 2 pi root over m by k cos square theta. Our people often do this whenever you find a system like this, they find an effective diagram like they shift the spring along the groove saying the spring constant is k cos square theta. Aniket, you getting it?
Yes, sir.
So like in a problem like you asked, what if they're at an angle to each other? Let us say, wow, yeah,
Sir, the effective one I didn't understand completely.
like effective one as in like the time period is anyway right coming like this. So I can consider the spring block system is like this, right?
Okay, sir.
Yeah. So whenever you find a system like this and somebody says the spring block system is only oscillating like this, let us call this as K1, K2, and this is theta. The spring block system is only oscillating like this. So I effectively write this diagram as, can you give the spring constants?
Yes, sir.
K1,
K2 cos theta.
cos square theta.
Oh, cos square, sorry.
Do you forget that? Okay, it's not like you're writing components. It is writing an effective spring constant, that's all. Okay, don't ever forget and put cos theta. It's always cos square theta. You're not writing the component for spring. Okay, you can't write for a component for a spring. Spring
But
is
I
not a
still
force.
didn't
You
get the
can't write a
cos square theta part, sir.
what?
So why can't we write component for spring?
Spring is not a vector. Spring is a body. Can you write a
Oh, okay.
component for you? Like, is there a component of Aniket? Stupidity component and
No,
real.
understood, sir.
I don't know if there are components like that. We should. I'm pretty sure the stupidity component of you is like really big.
No, sir.
So at an angle, yes, you can do this for sure. But important point is don't ever worry that whether there is gravity, whether there is an external force or anything like that. Okay. I think it is too much for it to one day. We've already learned too much today. I suggest you for today to get into HC Verma. Obviously, try the problems in the first page. Leave out simple pendulum just for today. I'll let you know if it is there in the exams or not. Just leave it out. Aditya, 1 second. So try the questions in this page, and when it comes to this page, question number 14, 15, 16, don't try yet. 14, 15 only. Don't try them yet. You will find it a little difficult. 14 and 15, they're easy only. You might find it difficult. 16 you can try easily, but 17, 18, 19 you can just do whatever you want. 17, 18, 19, 20, 21, 22, and the page next page questions.
So 19th one, we might need your help specifically.
What? Where? No, obviously you just did like you
You'll have to
asked the
take the
question, like,
components.
Yes,
You have
sir.
to take cos square theta.
yeah.
Sir, but I
So
didn't understand that cos square theta part. So like why cos square theta? I didn't get it properly.
let me take you there. Somebody else also said the same thing. Oh, it's you only, right? I displaced it by x. Spring is expanded by kx cos theta. So the restoring force, sorry, the spring force is kx cos theta, but you should take the restoring force along the oscillation. So I take the component of the force again. So kx cos theta into cos theta, f cos theta. You get it now?
Not
Vamshi.
exactly.
Yeah, Sharad.
So not exactly, sir. So like first time will be x by cos theta, right, sir?
No. If you write x by cos theta, I'll show you what it is. Okay. If this is x, it is very small. You're talking about this.
Okay,
Okay.
sir. Okay, sir. I took another
Exactly.
triangle. Like I
Yeah.
took the
So
wrong one.
you get the point now. This is theta, so this will be x cos theta only. If you take x cos theta, it will come something around like this. You take a right angle triangle like this, and this will be the x cos theta. That's not the expansion of the spring, right?
Yes, sir. Understood it.
Yeah. Aditya, what is it?
Sir, in DPP, sir, I tried, sir, but I have to leave many questions in between, sir.
You'll
Yes,
slowly
sir.
get them.
Many concepts were not taught. That's why, sir.
So yeah, you will slowly get them. Tomorrow I'll teach about the simple pendulums and all the other stuff. For today, you have a lot of homework, so try doing them. Tomorrow we'll get to talk about the simple pendulums and other kind of SHMs, and then there is more to talk. So let me end this topic for today. Any more
Sir,
doubts
one more
just
thing,
regarding the
sir.
topic?
Not topic, sir, like one permission, like
Then we'll
for
talk.
today,
Then
can I
we'll talk.
neglect DPP?
Shut up. Sir. We'll talk. Okay. Just regarding the topic, if there are no doubts, I'll just stop the recording and we'll meet tomorrow. All right.